Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus 2, where we are forging a bold new way of thinking about differential calculus. In Algebraic Calculus 1, we basically set up integral calculus in a new way. Now it's time for the differential calculus, which is more subtle, more difficult than the integral calculus. Okay, a crucial part of this story is to move towards so-called infinite series, but we have to think about these things in a correct way. So this is a very major challenge that has yet to be overcome. So we're going to be talking today about index degree, which is a really important notion that allows us to formulate a multi-series theorem. And we're thinking of having an ascending level of theorems, starting with the binomial theorem, moving to the multinomial theorem, which we talked about in our last video, and now today to the multi-series theorem, which is a bigger, broader picture. So the crucial new concept of index degree occurs in also the solving polynomial equations series of lectures, which are available for members at the Wild Egg Maths channel. And there I basically solve one of the most important historical problems in all of mathematics, which is how to solve polynomial equations in a very general fashion. So I go in a completely different direction from the usual solving by radicals story, which is just not the right way of thinking about it, okay? The right way of thinking about it is through polyseries, and to look at things like the combinatorialists do. And in fact, it turns out that there's intimate connections with a lot of beautiful combinatorics coming from a massive generalization of the Catalan story. So if you're interested in this general trend of thinking, you would, I think, really benefit by going through this solving polynomial equations series, which is sort of hands-on and discursive, and I sort of, take you with me along on this journey. Okay, so what's the multi-series theorem basically about? Well, the idea is to replace a possible infinite sum to a power like this. We're trying to understand, does it make sense to extend the multinomial theorem to have an infinite or an unbounded number of entries? Instead of going up to a finite sum, can we have an ongoing sum and still try to raise it to the nth power, where n is a natural number? Well, there's all kinds of problems with that. And one way to get around that, or to minimize the problems, is to convert it into a question about polyseries. So we make a subtle shift and think, instead of having a sum like this, we think of having a polyseries, which we'll write C0 plus C1 alpha plus C2 alpha squared and so on. Okay, so this is like a polynomial or a polynumber, but that keeps on going, higher and higher powers of alpha. And notice that we're starting with C0 because that's in keeping with having powers of alpha. So now we have moved to replacing numbers with polynumbers, but there's only a single polynumber variable alpha here. The advantage to that is that this alpha allows us to introduce the idea of a grading. So we end up with this situation which we can think of as a ladder. Okay, it's like a ladder going up. There's rung 0. Rung 1, rung 2. The powers of alpha clearly delineate this ascending ladder of complexity. And the idea is that we can try to get at what this thing is by attempting to understand what happens up to any finite level. Okay? We're not really ever in possession of the whole thing, whatever that even means, but we aspire to understanding this up to some arbitrary finite level. Okay, that's our approach. And so the use of the alpha here is crucial in that it introduces this grading, or you can think of this as this ladder-like aspect to the situation. So introducing this polyseries point of view allows us also to look at the binomial theorem and the multinomial theorem in slightly kind of a new fashion. So let's go back to the binomial theorem with just two entries, but instead of having a1 plus a2, or x plus y, let's think of these two entries as being the first two entries in a polynumber, C0 plus C1 alpha. So if we square that, say, we get C0 squared plus 2C0 C1 alpha plus C1 squared alpha squared. And the powers of alpha naturally sort of allow us to write this in a sequential, organized fashion. If we go to a third power, then also the same kind of thing happens. So we get C0 cubed plus 3C0 squared C1 alpha. That's the linear power. Then 3C0 C1 squared alpha squared plus C1 cubed alpha cubed. So in the binomial case, not really much difference happens. It's just that these powers of alpha allow us to sort of clearly organize the various terms that are involved. However, when we go to the trinomial theorem and look at this graded sort of interpretation of it, then we see things a little bit differently. So let's look at C0 plus C1 alpha plus C2 alpha squared. Okay, so we got a little basic trinomial, but now expressed as a polynumber in alpha. And let's say raise it to the second power. Now, when we do that and then write it out in increasing powers of alpha, we get this expression here. So the constant thing is C0 squared. The linear part is 2C0 C1, the product of these two terms. And then the alpha squared component will have a 2C0 C2 coming from the product of these two, and a C1 squared also. And then there will be an alpha cubed term, which will be 2C1 C2, and an alpha to the fourth term, which is obtained by squaring this one, C2 squared. So when we write it this way, we don't get exactly the same form as we did with the trinomial theorem in sort of the usual form, where you write it typically as the sum of the squares of the entries, and then 2 times the sum of all possible products. Okay, so that's not what's happening here, because here, this term here has 2 things involved in it. One is a square, and another one is one of these 2 twice products. Okay, so it's a slightly different take. You get to see this theorem in a slightly different way when you take this graded approach. So let's go one step up, taking this trinomial and raising it to the third power. So now we have the following result. So there's the constant term, a linear term, the quadratic term looks like this, the cubic term looks like this, the quartic term like this, and then there's the 5th degree and 6th degree terms. So you will probably recognize the same ingredients, but they're organized now in a different way. And if we look at this and say, what's the pattern here? It turns out that there are 2 sort of important constants associated with any one of these terms that sort of tells you, what is appearing and why. And the first of these is a familiar degree. If we take some expression, a trinomial monomial like this, C0 to the K0, C1 to the K1, C2 to the K2, then the degree of that is just the sum of the exponents, K0 plus K1 plus K2. All right, so this term here has degree 3 because 1 plus 2 is 3. This term here has degree 3 because 1 plus 2 is 3. In fact, all of these have degree 3, as they have to, because we're really taking this trinomial and cubing it. It's because we're raising things to the power of 3, so everything that appears is going to have degree 3. Now, the new, or not really new, but for us, the crucial new sort of invariant is what we're going to call the index degree. Okay, so this is another kind of degree, but it's a little bit more subtle, and it takes into consideration not just the exponents, but also what the variables are that you're raising. Or in other words, it really takes into consideration the indices here as well as the exponents. So what is the index degree, denoted IDEG, of C0 to the K0, C1 to the K1, C2 to the K2? We'll define it to be this 0 times K0 plus this 1 times K1 plus this 2 times K2. And if there were more terms, it would just go on in the obvious way. Okay, so what is the index degree of this thing? Well, it's 0 times 1 plus 2 times 2, which is 4. What's the index degree of this thing? It's 1 times 2 plus 2 times 1, which is also 4. How about here, the index degree? Well, 0 times 1 plus 1 times 1 plus 2 times 1 is a total of 3. Index degree here is just 1 times 2, it's 3. So these all have index degree 3. These ones have index degree 2. This one has index degree 5 because 1 plus 4 is 5. And this one has index degree 6. And this one here has index degree 1. And this one has index degree 0. So you see that it's the index degree that tells you which of these various terms in the usual trinomial expression get attached to which powers of alpha. And it's kind of obvious why, because if we're looking at a possible constituent in the cube of this thing here, then the index here that's appearing is always the same as the power of the alpha that's multiplying it. Okay? So if we raise this thing to the second power, then we're getting a c2 squared, and we're also getting an alpha to the fourth. So the index degree of c2 squared remembers the power of the alpha that's involved. So there's nothing really mysterious about why this works, but it is really important to identify that this is an interesting and important number associated to a monomial, because it allows us to organize this graded trinomial theorem. Okay, let's have a look at what we might call the graded quadnomial theorem. Not sure if that's the right word. Binomial, trinomial, quadnomial. So here we have 4 terms, and we're raising it to some power. But the terms are organized as a poly number. C0 plus C1 alpha plus C2 alpha squared plus C3 alpha cubed. And let's raise it to the third power. Okay, so you expand it out and you put everything in the right form, and you get something like this that starts this way. Okay, so here's a constant term, linear term, quadratic terms, cubic terms, quartic terms, fifth degree terms, but it's going to carry on, right? Because it's going to go on up to degree 9 in alpha. So, but let's just have a look at this to make sure that this coincides with what we've already established in the previous case. So let's say look at this this thing here. Okay, so first of all the terms are of degree 3. In fact, all the terms in the entire thing are of degree 3, and that has to be because we're raising this thing to the third power. What about the index degree of these guys? So the index degree here is 1 plus 2 times 2, which 1 plus 4, which is 5. And let me remind you, so this is what you get when you take one of these terms and 2 of these terms. Okay, so we, in this product, we take 1 of these and 2 of these. Okay, so we're going to get C1 times C2 squared as the coefficient, but the power of alpha is obviously going to be 1 from this one plus 2 times 2 from this one. So that's 5. The power of alpha is just going to be the index degree. So similarly here, C0, C2, C3, the index degree is 0 plus 2 plus 3, that's also 5. Here the index degree is 1 times 2, that's 2 plus 3, that's 5. Okay. So again, the index degree nicely puts all of these coefficients in their correct place when we think of this quadnomial theorem in a graded fashion. Okay, so now let's take the jump to the multiseries theorem, where we are no longer raising a finite poly number to a power, but rather raising a polyseries to some power. Okay, so now what's inside the brackets is a polyseries with terms that keep on going in that direction. Okay, C0 plus C1 alpha plus C2 alpha squared plus C3 alpha cubed, and so on. And we're raising this to the third power in this case. Okay, and we've looked at this before, and here is what you get. Okay, at least up to terms of degree 6. In fact, I think I gave you this as an exercise, so you can check whether what you got is the same as what I've gotten here. Let's actually look at this thing here. What are these terms here? So these terms are characterized by, first of all, everything's still of degree 3 because we're raising things to a third power. So every term that appears here is going to be of degree 3. But it's the index degree that's going to be telling you where the terms are going to be appearing. So I claim that all the terms that are appearing in this bracket here as a coefficient of alpha to the 6 have index degree 6. Okay, for example, this one has index degree 6. 1 plus 2 plus 3 is 6. Here, 2 plus 4 is 6. 0 plus 2 plus 4 is 6. 0 plus 1 plus 5 is 6. 0 plus 6 is 6. 0 plus, oh, that's 5, sorry. Over here, 0 plus 3 times 2 is 6. 2 times 3 is 6, all right? They all have index degree 6. These guys all have index degree 5, index degree 4, index degree 3, etc. And crucially, let's say if we're interested in the component of alpha to the 6, none of the terms in this ongoing series past the alpha to the 6th term here will contribute. In other words, c sub 6 is going to be the biggest thing that appears in this coefficient of alpha to the 6th. So as far as just going up to this stage here, we could have done that by replacing this ongoing series with a finite series. We could just have gone up to degree 6 and truncated at that point. So we've gone up to c sub 6 alpha to the 6th and truncated there and just taken the cube of that. That, of course, would have given us more terms than just alpha to the 6th. But doing that and then just sort of cutting off everything with powers bigger than alpha to the 6th will give us this correct quantity there. So the beauty of this graded story is that if we're only interested in the answer up to a certain degree, we can evaluate that by converting the seemingly infinite ongoing sum into a finite sum. Okay? We can restrict ourselves up to the degree that we're interested in, then do the computation, and then further restrict to terms of degree, whatever we're interested in. Okay, so it may look like we're doing an infinite amount of work, but up to any point, it's always just a finite amount of work. And this is the crucial thing, okay? This is absolutely the basis for all correct mathematics, is that ultimately you are not allowed to pretend that you can do an infinite number of things. So we may be tackling something that looks like it might be infinite or ongoing, right? But we're doing so in a measured way so that at every stage we only have to climb up a certain height in this ladder. We never have to say to each other, okay, so now let's climb up to the top of this infinite ladder. Okay, that doesn't make any sense. The ladder just keeps on going. There is no top to the ladder. It does not make any sense for us to say or to use some phrase, whatever it is, that allows us to pretend that we're at the top of the ladder. No. Okay, so it's really important to appreciate that this graded aspect of the story that I'm presenting here allows us to do this, I think, very clearly and smoothly, restricting ourselves to things that we're actually logically allowed to talk about. Okay, so an important part of the story, though, that we haven't yet decided on is how do we determine the coefficients that appear in front of these various terms in this multi-series expansion. So for example, the one we were just looking at, where we have this polyseries to the 3rd power, so n is equal to 3, there was a whole bunch of stuff, but here is part of the alpha to the 5th expression. So there were some terms 3 c1 squared c3 plus 6 c0 c1 c4. So we're interested in these numbers, the 3 and the 6. Okay, where do they come from? Well, it turns out they are just multinomial coefficients. And it turns out that we don't have to do anything in addition to what we've already understood in the multinomial theorem to determine these coefficients. So let me explain that. So let's look at this c1 squared c3 term, okay? So how are we going to get that kind of term multiplied by alpha to the 5? In fact, we know that this term will appear only with an alpha to the 5th in front of it. So here are the 3 terms that we're multiplying together because we're cubing this entire thing, and they're all ongoing. But let's just have a look at the initial parts. So how could we get a term involving c1 squared times c3? Okay, so we need to pick up a c1. We need to pick up 2 c1. So maybe that's c1 and that's c1 times that c3. Okay, that also gives an alpha cubed. So and yes, indeed, we'll get an alpha to the 5th. So there's one way of doing that. But another way is to choose this C1, that C3, and that C1. And another way is to choose that C3, and that C1, and that C1. And those are the only ways of doing that. And what this really amounts to is, if we think in terms of boxes, okay, these boxes are representing the number of C1s, number of C2s, and number of C3s that appear in any one of these terms. So in this case here, we are looking to put K1 equals 2 things in this box, K2 equals 0 things in this box, and K3 equals 1 thing in this box. And the things that we're choosing from are really the factors that we have that are being multiplied together. There are 3 factors being multiplied together, and we have to pick from those 3, 2 of them to go into the C1 box. And we have to pick 1 of them to go into the C3 box. So this number here is going to be a multinomial coefficient. It's going to be 3, because there's 3 of these factors, and we have to choose 2 and 1. You could also write 2, 0, 1 to be completely pedantic. And that, of course, is 3 factorial over 2 factorial, 1 factorial. That's equal to 3. So that explains why we are getting this 3. And for this term here, C0, C1, C4, so we have to pick a C0 from one of these, we have to pick a C1 from another one, and we have to pick a C4 from the other one. So in this case here, we're ending up having to, of these 3 initial factors, one of them has to go into the, sorry, my boxes should be labeled slightly differently. Well, let me just put another box here, okay? There's the 0 box. Right. So this box corresponds to C0s, C1, C2, C3, C4. Okay, so what we need is we need to put 1 of those in the C0 box. In other words, we have to choose 1 of these factors to go into the C0 box. We have to choose 1 of them to go into the 1 box, and we have to choose 1 of them, so that'll be K sub 4, into the 4 box, and the other ones are all 0. And so the number that we're needing here, well, it's going to be 3 because there's 3 boxes, and then we have to choose 1, 1, 1. That's 3 factorial over 1 factorial, 1 factorial, 1 factorial. That's 6. So happily, the coefficients that are appearing in this multi-series expansion are just the regular multinomial coefficients. And if you've understood the multinomial theorem, then it's exactly the same kind of calculation that's involved here to compute these various coefficients. All right, so let's have a stab at writing down the multi-series theorem, where we're taking an ongoing polyseries, C0 plus C1 alpha plus C2 alpha squared plus C3 alpha cubed, and so on, and raising it to the nth power, where n is a natural number. Maybe I might make that explicit, because later on, at some point, we're going to be interested in, could we possibly make this a rational number? But for now, more modestly, n is just a natural number. Great. Okay, and what we think this is going to be. This is going to be another polyseries. So it's a polyseries in alpha. So it's an ongoing series in alpha, powers of alpha to the m going starting from 0 and increasing. And then here are the coefficients. The coefficients of the various alpha to the m's are themselves expressions in the various coefficients, C0, C1, C2, C3, etc., along with some coefficients. Okay? So what's in front of alpha to the m is itself a sum. And we're summing terms of the form C0, K0, C1, K1, C2, K2, C3, K3, etc., okay, with some coefficients. And what values of K0, K1, K2, etc. are we considering? Well, first of all, they should all be positive. I don't think I said that. I should say that. So let me put a 0 less than or equal to k0, k1, k2, etc. Right? They're all natural numbers. And they should all sum to n. In other words, the total degree here should coincide with this power n that we have up here on the left-hand side. So that's a condition on the k's. And now, however, there's an additional condition. This is the degree condition. Here is now the index degree condition. Okay? The index degree condition is that the index degree of this should be equal to m. What's the index degree of this? Well, it's 0 times k0, but I'm not going to write that because that's obviously 0. So it sort of starts at k1. 1 times k1 plus 2 times k2 plus 3 times k3, etc. equals m. Okay, that's just a reflection of this fact that if we're choosing, in these various factors, there's n factors, and we have to choose various terms to make a particular constituent term in this sum. Then every time we choose one of these terms, the power of alpha that we're getting is exactly the same as the index. And so if we take this particular expression, c1 alpha, say to the, find it 7 times in this big product, then we're going to get c1 to the 7, and there'll be an alpha to the 7 multiplying that. So the power of alpha that we're getting is 1 times 7. And if we say get c2 to the 13, okay, then raising this thing to the 13th power, we're going to get an alpha to the 26. So 2 times 13 is 26. Okay, so the sum of all the powers of alpha has to be equal to m. Now, before I discuss the coefficient, let's make the very important note that it's this condition here, the index degree condition, that guarantees that this is a finite sum. Okay? It may look like, okay, there's an ongoing number of terms here, but it's not. This is a finite sum of terms which are products of the CIs. And the reason is because this condition here guarantees that we're not allowed to use a ki which is more than km. The biggest ki, like k1, k2, k3, k4, how far out in the k's could possibly we go to have a constituent here? Once we get to k sub m, the coefficient of that is m. So we get m times k sub m. So if k sub m is not 0, then we're going to get m. Okay? Now that's still allowed because that's fine. But if we go 1 beyond that, we'll have an m plus 1, and the coefficient will be m plus 1, and that will overwhelm the right-hand side. So k sub m is the maximum number of km's that we can get. And this term here ensures that any one of these values of the ki's, the k0, can't get beyond n. So the maximal possible individual value of any of the ki's is n. So we have a bounded number of ki's up to m, and the maximum possible for any one of them is n. So these two conditions together make this a finite sum. So maybe I should put an arrow here, because actually both conditions are involved in deducing that this is a finite sum. And finally, what about the coefficient here? Well, that's just the multinomial coefficient that we've seen. Okay, we're raising something to the nth power. There's the n, and we're seeing how many ways can we choose these products so that we get k0, c0s, k1, c1, k2, c2s, etc. So that's the same problem of putting these n objects into these various boxes, m boxes, so that k0 goes into the first one, k1 goes into the second, k2 goes into the third, etc. And all of the n's end up in one of the boxes. And that's exactly the multinomial coefficient, and choose k0, k1, k2, etc. This, of course, is a finite list of k's, actually. All right? So this is the multiseries theorem, which, of course, ought to get a lot more press than it usually does. It is a core algebraic ingredient, extending the binomial theorem, extending the multinomial theorem, and moving us into the world of polyseries in a reasonably honest fashion. Okay? So a really important result. So there's much to learn. I'm Norman Wildberger. Thanks for listening.